Welcome to Chemistry 112. Quick reminder, today in lab we will be doing Group 2, we'll be doing Lab 3, the Kinetics Lab. Don't forget to be working on those online labs. Maybe turn one in before too long. It's getting close to the end of the year and you don't want to leave them all to the end of the year. But with that in mind, go ahead and finish this chapter. Going to maybe look at some homework, maybe look at some of the old tests. Next test is probably going to be next week sometime. I'm going to send out some like survey monkey document, try to figure out the best time. But what I'd like to do for the test is figure out a time, maybe like 6, 7 o'clock, give you a 2-hour period, come in, take the test, 7 at night, by the way. Come and take the test. That way I can kind of like all watch over you and do all that. If none of those if the time we all kind of collectively decide on does not work, I say, come, let me know your schedule, come in during the day, either that day, a day earlier, or the following day. I want to knock it out all at once. It's going to be sound like 20 questions, but most of it multiple choice. Like 95% is like multiple choice. So you got a pH problem. Find the pH of this solution. I give you all the equations you need to know. Give you some scratch paper. And there's 4 options to choose from. Instead of plugging it in, showing your work, pretty much you can, even if you don't know, you can at least guess on most of these. Over. So I'll send out a survey monkey survey or something to everyone's inbox a little bit later today. I'd like to try to figure that out maybe by the end of the week, so we can plan that for next week. Okay, let's go ahead and get started with this lecture. Okay. Got to pull up the PowerPoint. There we go. So, the last major topic to talk about is KSP. KSP is where, when we talked about the Ka, it was the K of the acid dissociation. Well, the KSP is the K of salt precipitation or solubility product. It's probably the more common term. Now, maybe you remember from Gen Chem 1, maybe you don't, but there are certain salts that are not quite so soluble, such as silver chloride, magnesium hydroxide, iron carbonate, almost anything with an oxide or hydroxide. Almost any sulfides are insoluble. And there were some rules you could learn. There's a chart you could read. All that told us if I mix these two things together, they would precipitate out. However, there was some math associated with it that we never really got to. There was just a K equilibria that the solubility is actually determined by the K of the solubility product, saying that essentially there is a set amount of salt that can dissolve based on a chemical reaction. In the case of these insoluble salts, the KSP is incredibly small. So when the KSP is really small, remember, that means it's very much so reactant favored. And so very little amounts of product will form. And thus very little amounts of salt will actually dissolve. Now, the general reaction for solubility is as follows. Silver chloride solid goes reversibly to silver ion and chloride ion. Now, writing the KSP expression, you got to remember it's products over reactants raised to the power of the coefficients. And we do not include pure solids or pure liquids. So that means the silver chloride solid does not actually appear in our general expression. The solubility only depends on the aqueous and gas phase components. So what that means for us is that regardless of how much silver chloride I put into a solution, only so much will dissolve. There's only two ways to change that. One is to change the temperature, thus changing the K. Remember, the only way we can actively change a K is changing the temperature. And we'll get to why that is next chapter. But so changing the temperature will change the solubility. The other way is to change the volume. While changing the volume does not change the K, if I add more water, it would lower the molarity. If I lower the molarity of all things involved, well, then we've essentially Le Chatelier'd decreased the products. When you decrease the products, Le Chatelier says we shift to form more products. So adding more water just lowers the concentration, so we have to shift over to get the concentration back. This works with everything. This works with sodium chloride. Sodium chloride has a very high solubility in water, but there is a point where it becomes saturated. The only way to increase the level of sodium chloride dissolved is to add more water or heat it up. Same thing with sugar. Sugar doesn't break apart. Sugar is just a 1-to-1. This is the max amount of sugar that can dissolve. The only way to change that is to heat it up or add more water. But so for the KSP for silver chloride, you would get this expression, KSP equals Ag times Cl. And we have a KSP for this of 1.8 times 10 to the negative 10th. Now this would actually means that only 1.3 times 10 to the negative 5th molar silver chloride could dissolve. Breaking this down, this means with this poorly soluble salt, we would only get 1.9 milligrams in a liter. That's how much silver chloride could dissolve in 1 liter. Not a whole lot. But how do we actually calculate that? This comes to where the ice table comes into play. However, because we have a solid on the left, it makes everything so much easier. You're going to assume we start with all reactant, no product. As we hit the change, we see a decrease in reactant, an increase in product by a factor of X. But since silver chloride is not included, we can just leave it blanked out. And finally, so we have at equilibrium, we have just X squared. Just X squared. So X is the concentration of silver. X is the concentration of chloride. With that in mind, plugging them into the KSP expression, you just get KSP equals X times X, or X squared. So if we're solving for the X, all we have to do is square root the KSP, and that would give us the concentration. And that's how we got that number on the last page. But what about if we have something that isn't a 1-to-1 ratio, like a 1-to-2 or 1-to-3 or 2-to-3? Then we have to do it a little bit more complicated because one, the KSP, remember, is products over reactants raised to the power of the coefficient. And lead chloride, you would produce 1 lead and 2 chlorides. So the KSP is Pb2 plus and Cl minus squared. When you write that ice table, we also have, for every 1 lead that dissolves, we also get 2 chlorides. So we get 2x, not just 1x. So plugging that in, x times 2x squared, this whole thing becomes 4x cubed. So for the KSP of 1.7 times 10 to the negative fifth, you would first have to divide both sides by 4, and then take the, not the square root, but the cube root of it. Now, how do you do the cube root on your calculator? That depends on what calculator you have. If you have a graphing calculator or a fancy calculator, you probably have a cube root button. But if you don't, one way to do a square root or cube root or all that stuff is raising a number to a fraction. If I raise it to a fraction of 1/2, that is the same as a square root. If I raise it to the fraction of 1/3, that is the same as a cube root. So we can do that even on a simple phone calculator. And that will solve for x. Though keep in mind one simple thing. X is the concentration of lead. It's not the concentration of chloride. Chloride is double that amount, because looking back at our ice table, lead is x, chloride is 2x. So we'd have to, if I ask you what is the concentration of chloride, you'd have to double that. If I ask you for the concentration of lead, it's just x. So let's look at barium sulfate real quick. Barium sulfate, and that's 1.08 times 10 to the negative 10th. That's our KSP. So what do we have to do here? Go into the doc cam. You don't really need an ice table, but it's just being safe right now, just to show all the steps until you get used to it. This splits apart. How does barium split apart? Barium splits apart into 2 plus and SO4 2 minus. Now, because this is a solid, we don't need to worry about that. But at I, before we dissolve it, there's 0 amount quantities of barium, 0 quantities of sulfate. Now, when this splits apart, this would be minus x, and this would be plus x, plus x. And so when we sum these two parts together, we get x and x. Our KSP expression would be Ba 2 plus, or SO4 2 minus, technically over barium sulfate, but because this is a solid, once again, we can ignore that. Because that's a solid, we can ignore that. Just like we did when we talked about the KW expression. That was all over water, which was a pure liquid. So what do we have? We have this equals x times x, which is x squared. So 1.08 times 10 to the negative 10th equals x squared. What do we got to do? Square root both sides. You do that, and you're going to get x is equal to, so I happen to have a square root button, 0.08 times 10 root negative 10. It's going to give you 1.04 times 1, 2, 3, 4, 5, 10 to the negative fifth. So that is the concentration of barium sulfate that could dissolve in water at room temperature. All I have to do, I have to figure out what is the ratios there. Set that up solve. It's actually a lot easier than some of the acid-base stuff, but it's a little new, and so we have to look at it a little bit different. Okay. Now, let's look at this one's crazy. This one is absolutely nutso. What is the concentration of lanthanum fluoride, LaF3, that would dissolve if the KSP is 2 times 10 to the negative 19th? This one's a little crazy because it forms lanthanum 3 plus and fluoride 1 minus. Okay. So writing the equation, lanthanum, fluoride, solid, splits into 1 lanthanum and 3 fluorides. ICE. Remember, this is, well, technically this is X. We're going to completely ignore that because it's a solid. This starts 0 and 0. Now, there's 1 lanthanum, so it's plus X. There's 3 fluorides, so we're going to have plus 3X. We have X and 3X. Now, our KSP expression is equal to lanthanum and times fluoride cubed, because it's raised to the power of the exponents. So plugging that in, we have X times 3X cubed. It's down a bit. So 3 times 3 times 3 is 27. 27 X cubed times X is 27 X to the 4th. So, and all that's equal to our KSP of 2 times 10 to the negative 19th. Okay. So the first step is divide both sides by 27. Pretty straightforward. You divide both sides by 27 and to separate the X. You have X to the 4th equals 7.4. We'll say 7.4 times 10 to the negative 21st. And then we have to 4th root. Now, you may not have a 4th root button on your calculator, but a 4th root is the same as 2 square roots. You can do a square root twice and get the same result. So you can do it either way, but I have a 4th root button, so just type a number 4, and then I have to type number 4, then the X to the power. Okay, 7.4 is 10 root negative 21. And we get X is going to be 9. We'll say 9 because it's technically only 1 sig fig right there. 9 times 1, 2, 3, 4, 5, 6. 9 times 10 to the negative 6. That is equal to X. Now, however, if I'm asking for the amount of fluoride dissolved, fluoride is not X. Fluoride is, once again, 3X. So the answer for fluoride would be 3 times that. Or essentially 2.7, we'll just round it to 3 times 10 to the negative 5th F minus. As I said, that one is the hardest thing I could throw at you, and I'm not going to be throwing anything that hard at you on some test. But pretty much all these problems, all KSP problems are essentially the same. There's not, they can fit into one of three categories: a 1-to-1 ratio, a 1-to-2 ratio, or a 1-to-3 ratio. The 1-to-1 and the 1-to-2 are the most common. So if you know how to do a 1-to-1 or a 1-to-2, the only thing that differs between those two is really the KSP, the actual number you have to square root. So they don't really change. Now, there is something of a common ion effect. The common ion effect has to do with Le Chatelier's, that kind of like a buffering effect. The common ion will have the same effect on KSP as it does with weak acids. For example, in silver chloride, if there's a lot of a common salt like chloride in solution, we will only have, you will have a lot less silver capable of dissolving. The KSP expression we just wrote assumed we have 0 silver and 0 chloride. What happens if you have a little bit of chloride already? Well, that means less silver could dissolve because we already have some chloride there. The same is said for basic insoluble salts like magnesium hydroxide. In basic conditions where hydroxide is already present, magnesium hydroxide is less soluble. But on the counterpoint, if you put magnesium hydroxide in acidic conditions, it's more soluble. Because like Le Chatelier's, when you add acid, when the hydroxide dissolves and forms, it gets neutralized. When you neutralize the product, what happens? You're removing product from solution. When you remove product from solution, Le Chatelier's says we shift towards more products. Now there's one more slide, and we won't really talk about this too much, but there are a K for complex ions. Complex ions are just charged aqueous compounds that are formed through Lewis acid-base reactions. Not this week in lab, but next week in lab, we will be looking at one of those. And we kind of looked at one of those on the test, iron thiocyanate. But there's many different complex ions: nickel hexaaqua, iron thiocyanate, silver cyanide. Basically, instead of forming a neutral solid, we're forming a charged aqueous species. But unlike traditional aqueous species, these guys actually are stuck together. Most aqueous compounds, when we talk about them, they are essentially solvated and separated. These compounds in themselves are actually, they're bound together chemically like an acid base, like actually bonded instead of just floating nearby. And so we have a K expression for the formation of these guys. They could be neutral species, they could be charged ions, but they're all aqueous complexes rather than solid salts, and they would essentially have a K expression like anything else. Formation can lead to. Now, where they can be of use is when they can lead to increased solubility of complex of insoluble salts. The example I'm going to give is silver cyanide will increase the solubility of silver chloride, because as silver dissolves, if there is cyanide in solution, it is then taken up through a separate reaction. And as it's taken up via a separate reaction, we have less silver dissolved, and thus the amount of silver goes down. This same issue was brought up on question 1B of the test. We looked at iron thiocyanate. If iron chloride, if I add chloride to solution and iron chloride can form, what would happen to the iron thiocyanate? The correct answer was the iron thiocyanate should have gone down as the dissolved as the free iron gets decreased in the form of iron chloride. So I just wanted to talk about that ever so briefly. But that is the end of this chapter. This was a lot of acid-base stuff and just a little bit KSP at the very end. Go to achieve. Okay. So let's look at some of the problems. There's only 15 problems. I know this isn't due for a while, but I want to show you some of the problems before we go to the old test. Like there's some questions asking just formation of a buffer. So which of these pairs would form a buffer? So to form a buffer, you want an acid and its conjugate, a weak acid and its conjugate base. So strong acid and conjugate base will not work. NaCl is a salt of the strong acid. Mixing a strong acid and a weak acid will not work. Mixing the conjugate base and a strong base will not work. Strong acid and a strong base will not work. Only one that would really work is HCN and NaCN. And a buffer solution is 0.21 molar in a weak base. Kb, blah, blah, blah. And 0.55 molar in the conjugate acid. What is the pH? Okay, so I'll do a quick buffer question. They give us a Kb 5.1 times 10 to the negative fifth. Let's say the base is 0.21 and the conjugate acid, pH plus, is 0.55. So writing the Henderson-Hasselbalch for a base, the equation looks as following, as I'll pull this up in just a second. For a acid, it was pH equals pKa plus log acid over base. For a base, it's going to be just the opposite. POH equals pKb plus log base over acid. The only thing we really have to do is turn the Kb into the pKb. And technically, really, what you're doing is you're just saying, you're just taking the log of these three things. You could just as easily do that math as well. And then find the OH, turn it into the POH. Whatever is more convenient for you, because you're essentially just setting up the K expression and solving for it. It gives you the same numbers either way. Same numbers either way. You just got to make sure you understand what math you're doing. So the concentration of OH is 1.95 times 10 to the negative fifth. Take the negative log of that to get the POH. The POH is 4.711. Now it asks, what is the pH, not the POH? So we're going to take 14 minus that. So the pH would be then 9.289. So 14 minus the 4.711. So the hardest part, there's a lot of repetition, If you learn how to set up these K expressions, there's a lot of repetition for these things. You just have to make sure you understand, am I working with an acid? Am I working with a base? Am I asked for the amount of acid? Am I asked for the amount of base? Can I convert between the two? As long as you recognize that, there's just a lot of repetition that goes on. Okay. So this one, they say like a phosphoric acid is triprotic with these Kas. Each of a buffer compound, blah, blah, blah. What? We're going from pKa. Yeah, I'm going to skip this one, but just since we're using this, a buffer mixed by the second and the third, we're going to use the Ka2. This is for the loss of the first proton. This is going to be for the loss of the second proton. So we're going to need pKa2. But then they're going to say, oh, calculate the moles of each one and then calculate. It's going to be a little busy work right there. Okay. Here's a real titration problem. There's two parts here. We have 25 mils of 0.35 molar base and 0.75 molar acid. They ask, what is the initial pH? And then what's after 5? So we're dealing with a base first, and then we are adding 5 mils of acid. So the first part, without anything else, is just log of the base would give us the POH. Negative log of the base would give us POH. So that's 0.456. We have to subtract it from 14 to get the pH. So 13.544 is our answer. That's why I'm saying you got to make sure you understand what you're dealing with. I have base to start. And that's going to give me POH. The answer asks for pH. We have to watch it. Go slowly and make sure. Now, the next part. I am going to figure out moles of base and moles of acid. Moles base, moles acid. So moles of base is going to be 25 times 0.35, 8.75. Moles acid, 0.75 times 5. That's 3.75. 2. What gets neutralized? Well, I neutralize 3.75 moles of acid with 3.75 moles of base. We have 0 acid left. We have 5 moles of base left. 3, we got to dilute. So we want to turn moles back into molarity. 5 divided by 25 plus 5, which is 30. So 5 divided by 30 gives us 0.167 OH. Then finally, what is the pH? We're going to have to take, running out of room. The pH, which is just the negative log of our OH, what gives us the POH, 777, 14. So I got in this problem 13.223. So for our two problems, There are two problems, 13.554. And then once I added 5 mils, I had 13.223. So for a strong acid, for a strong base with a strong acid, the pH didn't change very much. Once you get to equivalence point, the pH drops drastically to 7. Okay. So this is just hypothetically. This one just wants you to think of these guys. Okay, so this one we have a weak base and we're adding an acid. Weak base, we're adding an acid. What would happen? What would the pH be before I've added any acid? Well, it should be basic. So the pH should be greater than 7. Now, because this is a weak base, at the equivalence point, which you could calculate this, 60 mils at 0.25 molar, and that's 0.5 molar. At 30 mils, you would be at equivalence point. With a strong acid and strong base, this should be neutral. But with a weak base, this should be mildly acidic. So it should be less than 7. And then once I add more acid, it becomes completely acidic and just keeps going acidic. So that one's just a hypothetical one. So here's one. So this is a buffer one, but it's kind of like you have to treat it like a titration problem. I'm going to skip some of these. I want to do at least a KSP. Okay. Okay, this one's actually pretty easy. The half equivalence point occurs halfway at the equivalence point. The pH equals the pKa at half equivalence point. So since they give you the Ka, you just have to take the negative log of the Ka, and that's your answer. So, not supposed to be very hard there. Calculate the pH at equivalence point. Select the weak acid. There's a titration interactive. You actually have to titrate. You have to figure out the pKa by actually, you have to find the pKa by finding the half equivalence point. So you would titrate that like you would in lab. So, okay. Right now, that should be really easy. Classifying these guys, strong acid, strong base. You can look at those guys based on where the equivalence point is at and how sharp the curve, whether it's strong or weak. So that's pretty easy. And then we have, let's see, KSP, kind of KSP. A hypothetical one, which one of these is going to be more soluble in acid? That's a common ion effect. And then there's like looking at KSP strength. So I'll do one of these KSP ones. Okay. Okay, calculate the solubility of this compound in grams per liter. This is just a little bit more of a pain in the butt because it's asking you to, once you have it, to turn it into grams per liter. So we'll go through this one, and that's where we'll stop with the homework. So beryllium hydroxide, right? In the expression BeOH2 splits into Be2 plus and 2OH minus. We're going to have X and 2X as our E situation. Setting up our KSP, we have KSP equals x times 2x, all that squared. I have to write the KSP down as 6.92 times 10 to the negative 22nd. Okay. So working at this one, x times 2x squared is 4x cubed. Now, to get the x, we're going to first take our 6.92 and divide that by 4 to get x squared, or x cubed. By 4, that should give us 1.73 times 10 to the negative 22nd equals x cubed. Next thing we're going to do is cube root both numbers, and that will give us x. (73) times 10 root negative 22nd. You do that, you get x is equal to 5.6 times E 1 6, 7, 8. So 5.57 times 10 to the negative 8th. 5.57 times 10 to the negative 8th. That is the amount of x. Now, that means that is how many units of beryllium hydroxide dissolve. You could calculate the molarity of each one and turn each one into grams, or you could just say that's how many units of beryllium hydroxide and calculate the molar mass of that. So what is the molar mass of beryllium? Beryllium is like so, 4, 5, 6. I'd like to say it's 8. I'd have to double check. Beryllium is, nope, beryllium is 9. So Be is our 9. We have 2 OHs. O is 16. H is 1. So together they make up 17. So 9 plus 17 plus 17 is 43 grams per mole. Now, if molarity is defined as moles per liter, then to get to grams per liter, we have to multiply by the molar mass. 43 grams per mole. And that will give us moles per, that'll give us grams per liter. How many grams of beryllium hydroxide will dissolve? So we get 2.3, well, let's say 2.40, 1, 2, 3, 4, 5, 6, times 10 to the negative 6th. So I have 2.40 times 10 to the negative 6th as my mass. Let's try that. So 2.40 negative 6. So that one you just do like any other KSP, but you have to turn it into grams instead of leave it as moles at the end. But so there's not a whole lot of graph ones, but look at some of the graph problems on the homework, and we'll look at some of the graph ones on this test, because that's what we want to look at now. So the last test I did was a take-home test, which is not going to be what we're going to have right now, but questions are going to follow a similar thing, except instead of being all fill in the blank, there are going to be mostly multiple choice. So with that in mind, let's look at what last year's test looked like. Now, we have a titration graph of some kind. I'm asking you, expect sound like this. What is the concentration and what is the Ka? If it's strong, it will not have a Ka. If it's weak, it will have a Ka. How can we tell if it's strong or not? Shape of the graph and also where the equivalence point is at. Based on this, the equivalence point, I included all the lines to make it obvious. Equivalence point right here, this big jump is at pH 7. pH 7. So not above 7, not below 7, right at 7. So this is a strong acid. So the part B, what is the Ka? The Ka is not applicable. We cannot find the, do not take, this volume right there is 17.5 mils. Do not take the half equivalence point, which would be what, like almost 9 mils, a little bit under 9 mils, and say like, oh, the pKa must be something like 0.92, and then try to turn that into a Ka. Don't do that. Don't do that. So, but what is the concentration? How do you determine the concentration? Well, I say there's 25 mils of acid. We don't know the molarity of the acid, but we do know there is the molarity of the base is 0.5, and based on the graph right there, how much base is added? 17.5. So this part, do not be confused. This should be the easiest thing on the whole dang test. It's just MaVa equals MbVb. Do not forget this simple concept from General Chemistry 1. MaVa equals MbVb. We have the Va. We have the Mb. We have just looked up we have the Mb. We just looked up the Vb. So what do? These two numbers divided by 25. These two numbers divided by 25. So 0.5 times 17.5 divided by 25 would give you the molarity of your acid is 0.35 molar. Easy as pie. No negative logs, no complex relationship, no ice tables, just plugging that in and solving. So, no. Now, determine the pH of the following substances. Now, in this case, since this was a take-home test, they had a book. They could look up if this was weak acid or not. On an actual test, you'll be given the Ka if this is weak or not. If this is weak, you'll be given a Ka. It'll be abundantly clear whether you need Ka. But because this was a take-home, I did not give that to them. They were expected to figure that out. So the first one is strong. It's a strong acid, 2,3 molar. The second one was a weak, nitrous. Let's see, I looked up some of these guys earlier. See how far values. Nitrous. HNO2, the Ka is, well, it's 7.2 times 10 to the negative fourth. Let's see. Then we have 16.6 molar of acetic acid. Acetic acid is gotta look those up. As 1.8 times 10 to the negative fifth. This one is super concentrated. If you haven't noticed, 16.6 molar. This is called glacial acetic acid. Holy cow. And H2. That one, that last guy, NH2OH, I think that's a base, if I'm not mistaken. That's hydrazine. I'd have to, let me look. And could be, let's see. Or it might be amide. Let's see. That might be just amide, which is a strong base. No. Hey, it's. Let's see. I'll just look up NH2OH. Hydroxylamine. Hydroxylamine, let's see. Wikipedia will actually solve that. Hydroxylamine is a, no, it's a base with 1.8, oh, sorry, 1.1 times 10 to the negative 8. That's a KB. And and then finally, we have 5 grams of sodium hydroxide in 1 mil. 5 grams NaOH in 100 mils. Okay, looking at those, some of them, you have the first one is strong, the last one is strong, the middle 3 are weak. So how do we go with the strong? The strong is straightforward as can be. For strong, all we have to do is take the negative log of our value. So the negative log of 0.023 is just going to be pH of 1.63. So we'll say 64. For the last one, the 5 grams of sodium hydroxide, you have to turn grams into moles. Sodium is 23, hydroxide is 17, it's 40 grams per mole, so 5 divided by 40 turns it into 0.125 molar divided by 0.1 liter makes this 1.25 molar. Negative log of 1.25 is a really negative log is negative 0.09. So this one, when you have to add 14 to this, 14 plus 0.09, 6, well, we'll say 10. You get, this one's actually above 14. This one blows the pH out of the water. And it's possible to have a pH above or below the standard scale. The standard scale is just for water. This guy is more basic than what we're used to because it's highly concentrated. Now this guy, Do we have to use an ice table? Let's look. 7.2 divided by -4. No, I don't think any of these we have to use an actual ice table. So what is the shortcut? The shortcut, you can set up all the work, but really what all the work comes down to is the concentration of protons is equal to the square root of Ka times HA. If you don't have to use an ice table, that's what this all comes down to. H plus is equal to the square root of Ka times HA. So the square root of Ka times HA, 0.72 times 7.2 times 10 to the negative fourth is 0.0228. Negative log of that also is pH 1.64. So the first guy and the second guy ended up having the exact same pH. However, you notice this one is the second problem is 31 times more concentrated than the first one. That's the power of the strong acid versus weak acid. The same pH, yet this is 31 times as concentrated. Let's do it again. H plus is equal to the square root of Ka times HA. What is the concentration of H plus? 16.6 times 1.8 times 10 root negative 5. You get 0.01. Let's see. We'll say 173. Take the negative log of that. 1.76. So these guys are all in the same pH range. You guys are all in the same pH range because of, well, that one's super concentrated, but it has a much weaker Ka. Now this one is a base. The same holds true. OH minus is equal to the square root of Kb times the amount of base. So if I take the square root of 1.1 times 10 to the negative 8th times 1.5, we should get the amount of OH. But you got to remember that's the amount of OH and not the amount of H. Make sure you know whether you're dealing with a Kb or a Ka. So that gives us 0.000128. 14 plus the log of that gives us our pH. So the hydroxylamine has a pH of 10.10. We'll say 10.11. 10.11. I know I'm going fast because we're going to go through some more of this on obviously Tuesday. We won't have a chance to finish this, but those are just examples of standard, no thrills, no real major difficulty of acid-base determine the pH problem. But let's just quickly look and see what other options we have, what other problems we will go through that we may not get to right now. What two compounds would you mix to form a buffer of pH 9.5? Use the solubility product to predict the concentration of the following salts. Another titration curve, this time with a weak base and a strong acid. Determine the protein of a pH solution. Determine the pH of the following buffers. titration problem. Because this was a take-home test, I asked more about titration. And then bonus was classifying these salts, but expect more salt questions. Oh, come on. Classify the following salts. So we'll get to how to do that again on Tuesday. But in the meantime, how would you answer this buffer question? Now, on the test, you'll be given possibilities. On this one, since it was a take-home, the possibilities are endless. What you have to do is you have to remember a buffer is only good within plus or minus 1 unit from the pKa. So you want pKa plus 1 minus 1. So you want a pKa somewhere between 8.5 and 10.5. If you did not find a buffer that was within that region, this answer would have been wrong. You had to find some sort of acid or base that had a pKa within that region, between 8.5 and 10.5. But there is multiple different possibilities, multiple different right answers. It all depended on where you looked and which one you chose. But on the test, there will be only one possibility that can answer this, because you'll have 4 selections. You have to look at the Ka, turn that into the pKa, find which one is closest to the desired pH. We will finish up with, we'll do number 4, and then we'll pick this up on Tuesday. Predict the molarity of zinc and zinc carbonate, and the amount of silver and silver sulfide. So once again, you had to look up the KSP values. KSP values. So so you really had to find a table, and you had to say, oh, I got it from there, and it really didn't matter as long as you stated where you got it, and I could find the same number. So silver sulfide is 8 times 10 to the negative 51st. And zinc carbonate is 1.46 times 10 to the negative 10th. Looking up on my table. So, yeah. So this one, it's going to split into a 1-to-1 ratio. So our KSP is just going to be X times X. So really, this one's just 1.46 times 10 to the negative 10th equals X squared. What do you got to do? You got to square root both sides. The first one's pretty straightforward. 46 times 10 root negative 10. You square root that, and you'd get the molarity of X, which is also equal to the molarity of zinc. It would be 1.21 times 10 to the 10 to the negative 5th. Now this guy, KSP equals 2x, all that squared, times x. So when all is said and done, you have 8 times 10 to the negative 51st equals 4x cubed. You divide both sides by 4, So you get 2 times 10 to the negative 51st x cubed. And then you cube root both sides. And that would give you x. 3 and for God's sake. 3, then 2 times 10 root negative 51st. You get is something like 1.3 times 10 to the negative 17th. And then you have to remember silver would be not x, but 2x. So silver is equal to 2x. So you get 2.6 times 10 to the negative 17th molar. So you have to be very careful what's being asked. But with that in mind, KSP, there's only typically 2 types of problems. It's either this or this. Those are the 2 versions you'll see. The only thing that changes is what is the KSP. So they're not really too difficult. Let's see. Word. Back to Word. So that was problem 4. Let's see. Yeah. We'll go ahead and do problem 5 just because this won't take very long. We titrated 12 mils of a base with 15 molar, 12 mils base, VB. We want to know what is the MB when we used 0.15 molar acid. Well, what is the volume acid? The volume acid, we see the big jump at 20. So the volume acid is 20. So we have 20 times 0.15 divided by 12, and that would give us 0.25. So the answer to what is the concentration of base, it's 0.25 molar. Now the other question is, what is the Ka? What is the Ka? Well, the pH is equal to the pKa at the half equivalence point. So even for a base, that's true. pH is equal to the pKa. So at 10 mils, what can we say about the pH? The pH is about at, we'll say 10.9. This is where it can be a little iffy depending on how well it's zoomed in. But 10.9, safe assumption. So what do we have to do? I'm going to go ahead and switch to the doc cam for this last one. But so, because I asked for the Ka, not the pKa. pKa, we'll say approximately 10.9. So how do we get the Ka? The same way, H plus is equal to the 10 to the power of negative pH. Well, Ka is equal to 10 to the negative power of pKa. So you're going to say Ka is equal to 10 to the negative 10.9. So 10 root negative 10.9 is going to give us a Ka of approximately 1.2 and 1.26 times 10 to the negative 11th. And that was the answer for that one. So we're going to go ahead and stop there. We won't get done with this today, but on Tuesday we'll finish this up. I'm going to, as a quick reminder, test is probably going to be next week. The test is essentially written. I'm going to send out a survey monkey survey about trying to figure out the best time to do the test. It's probably going to be in the evening. I'm going to take where people have the most overlap, where most people say, yes, I can do it on this evening, and do it then. If you cannot make it, if like say, I can only do it Tuesday and I cannot do it Wednesday or Thursday, and like I say, take it either the day before, day of, day after, get with me, figure out your schedule. We'll find some time for you to come in. Hypothetically, you could be taking it during your lab period as long as you're not in the group that is doing the lab. So we'll figure that out. I'm going to send the SurveyMonkey out today. You can take that survey today or tomorrow. I'd like to try to get it done by Saturday. Get it back into me and figure out when to take the test. So the end of the 9-week grading period gets done this Friday. So finish up all your work. And of course, don't forget to be working on those online labs. Okay, that's where we'll end it. We'll finish this up on Tuesday.